So first, thanks to organizing committee about giving chance to me to present something in this workshop, and especially thanks to Professor Manish Kumar Gupta. We have a long relation from IIT Kanpur, and previously two presentation also from IIT Kanpur professors. So those are very famous and also very interesting things have in their research. They have done a lot of research and is still going on. So today I just give you very little glimpse about fractals and chaos in differential equation, because I don't have any special work in and anything in differential equation, but I to connect something related to fractals and chaos inside the differential equation. So you will see that when you have differential equations, so these are coming from different places, you may have some application. So you know about me, and now what I do in this conference, I have just in this workshop. So I just tell you a little summary about that. So as we know that fractal and tools develop over recent years, which are utilized for solving more advanced scientific and technological problems. So these are not very old tools. These are new. Often variety of problems of physical process can be modeled into operation, which generally
I
lead to
think your
differential equation.
sound is, Sajid, your sound is a little bit difficult to hear. So maybe you can switch off the video. So then maybe, it will take less bandwidth.
No, I think, okay, just I speak little more, maybe.
Yeah.
So
Yeah, yeah.
generally, these equations are extremely difficult to solve analytically or much harder to analyze. It can visualize effectively through fractals. Moreover, the real problems, issues on frontiers of modern scientific and technological, economical, and social researches are nonlinear in nature. In many cases, nonlinear system, a small change in parameter can lead to sudden and dramatic changes in both qualitative and quantitative behavior of the system. Now, his voice is okay? Is it
Yeah, it
okay
is
or
okay. Yeah, it is okay. It is
okay?
okay
Okay.
now.
So recently,
It's
excel
okay.
studies on nonlinear dynamics show that chaos occur widely. So due to this reason, now many people interested nowadays in to explore the beauty of fractals and see the behavior of chaos inside the system. So these two things we will see here, and we will explore these through some application, and also we see these things inside the differential equation. So we come now here to see some pictures. These pictures are generated through some functions or equations or differential equations. A lot of things are available in the literature, but we connect here, try to differential equation. But first, suppose we have function, we can generate first picture, we have now generate second picture, third picture. I will show some of the picture how to generate. Okay. So now we see that here how much complex above pictures. First we see this. If we know about the complexity of the pictures, then we can find the things inside the picture, and we can see that this picture will be fractals, or inside fractals is there chaotic behavior. So complexity in the system is due to nonlinearity, irregularity, or roughness in the nature. We can find a solution of complex nonlinear problems using fractals and chaos. So what are fractals? How these appear in nature? How these useful in mathematical sciences? We will see these things. So fractals first. So in the fractals, actually, there is no hard and fast definition of fractals. This is very, very important. A lot of definitions are available in the literature, but some of them, see some there. On this, we will present something here. So no hard and fast definition of fractals. Fractals can be defined in terms of characterization of things. So fractals theory is in developing stage. So every few years, we have something more inside the fractals. Some more result I find in different ways, new kind of fractal. So these may be irregular shapes. Sometimes when we see the irregular shape, that may be fractal. There will be self-similarity. Our irregular shape, our self-similar may not be fractal. Okay, we have some things to we can say these are fractal. Fine structures. If we have fine structure, there may be fractal, and we have Hausdorff dimension is strictly greater than its topological dimension. Whenever we see the pure mathematical thing, when we have sets or something like that, we can find the Hausdorff dimension and also find the topological dimension, and we will see if Hausdorff dimension greater than strictly greater, then there may be fractal. Okay. So based on this, we will see the some pictures here. This first picture is just see that here is a self-similarity. Inside that, you check that we have this line. We have another kind of fractal that is a fine structure. Okay, there is fine structure. We go inside and inside we can see that we are getting a again similar kind of picture inside. So it is a fine structure. And we can see another kind of picture. We cut and go inside and cut and small. We see that last one is also a fractal. So these kind of things we have fractals, and we when we generate pictures through also we have many things behind that. There are many theory behind this. Also we have theorems or mathematical calculations. So we are not able to present many things here about mathematical relations and computation and theorem, but I will show you what are the fractals and how these appear in the we can see through differential equation. Okay. So how did question is how did we have a this type of picture? So how did manage to involve such complicated architecture inside the nature? So Mendel brought points is that complication exists only in context of traditional Euclidean geometry. As a fractals, branching structure can be described transparent simplicity with just few bytes of information. So we have very complex things in the nature. Okay, like so this is the some of thing I will see. Okay, like a turbulence motion. Okay, turbulence in fluids, or a lot of things we can see. Those things we like looks like very complex, or sometimes are very complex, but we can study through something. So here is we have some tool that is a fractal. So nature was regarded as noisy Euclidean geometry. So we have to change something inside the Euclidean geometry, and then we can study, then we can find the solution of complex problems. So mountain is not a cone, but like a rough cone. Fractal geometry is an extension of Euclidean geometry. So we extend some parts of the Euclidean geometry and we add some more kind of object inside the Euclidean geometry, then we have fractal. In Euclidean geometry, we have object like line, circle, and triangle, or like that. So we have in fractal geometry, we have cantus, set, frequency, triangle, a lot of new names. Whatever exist in old days, different kinds of objects. Now those have some name inside the fractal geometry, and we have some special kind of name, and we have those objects. We have some name based on some scientists, those who have discovered previously. So we have now next thing. First is coach curve. So first is coach curve. How to find coach curve? How to generate the coach curve? Given a line, just take a line. In base, take a line, and in this line, what we do? Just cut 1/3 part, and then we do that thing like that. So in this case, when we will see that here, we have line cut 2 places, cut 1 place, and put 2 segments. We do same thing on each part of a line, means on each segment we cut 1/3 and put again 2 same length line at angle, whatever chosen in the beginning. Okay, so same. So continue this process, then we get a fractal. That is a code. So here is we have repetition. So I am trying to first here give detail about fractals. Then after this I will give detail about chaos. Then I will connect both things with differential equation, and I will show some application of. Okay. So we have now another kind of fractal here, that is based on triangle. That is the snowflake curve. In this snowflake curve, we take a triangle. After taking a triangle, what we do? Just put again same way as previous picture. We cut 1/3 part and put here. Okay, we cut dot dot and put 2 green lines of same length. We do on each side of triangle. After doing this, we repeat this process. So we will see new this picture. What we have done again on the each small segment of the line, we have put 2 small lines on same way on previous step what we have done. So kind of we get this. So this is the last one is a fractal nowadays is called snowflake. This type of picture exists already in these type of picture exists in art and gallery and a lot of many places when we see old architecture. Okay, especially in India, we see this kind of picture exists, but that time there was different name based on some religion or something like that. Okay, but also these type of things also exist in many places. When you see around the beautiful arts in the books or many other places. Okay. But now we have this scientific name inside the mathematics snowflake curve. And now we have next fractal, that is a frequency triangle. So it is also based on triangle. What we do, we take a triangle. In this triangle, inside triangle, we will cut 1/4 part. If we will cut 1/4 part, so we get a new structure like this. So in this new structure, what we have now? We have a new, we have new 3 small triangle. but these are similar than above actual triangle, but these are small. So leave the white part, and on the black part we do again same process, cut 1/4 part, then we get this part. Next picture. After getting next picture, we continue same process and we delete again 1/4 part. So continue this process up to our requirement. Okay, we get a simplicity triangle. Maybe 20 iteration, 50 iteration, depends how much accuracy we need, how much complex picture we need. So this is a simplicity triangle. Now we have next one, frequency carpet. Before previous one was triangle, now we have carpet. Actually, mostly name are based on how picture looks like or who has generated like that. Here name is carpet. Is just we get a structure. Generally, this type of design available on the carpet. So they have given name like that. So we in this case we take a square. Now what to do? We again do similar way as previous picture. In the triangle we have middle. Here also we cut middle 1/9 part actually. 1/9 part. Why? Because this is a 1/9 part because we have divided this triangle in 9 part, and middle one is 1/9 part. 8 parts. But actually we have all 9. So in the other 8 part of small triangle, we continue same process like this. If we repeat the process, okay, we get now this. Right. Now there are many more. In the each small part, we have again 9 small squares, and cut one is removed. We are removing these many small squares. So we have this new picture, and again repeat same process on each part. We get this type of picture. So due to this reason, frequency carpet has the name carpet with this model or with this fractal actually. So this fractal is frequency carpet. So same way we have some other kind of fractal we can generate. This process may be apply in different way also. Now we cut in same way in 9 part, we cut remove the 4 part sides is white, we will remove. On the each small part we do same and process like we get fractal like. So there are various way to apply on a same object what we have chosen in the beginning. But you have different generator. Actually, first is we say what you are applying, that is a generator in a geometry. But when we have we can do this through also function. Then we have IFS. IFS means iterative function system. Then we can generate also this type of. So here we are doing through geometrically we are removing, but we can remove this through function also. So we can also take another kind of initial generator and continue the process on each small line, we get a fractal. So if we get this type of solution in a different solution of differential equation, some in the differential equation, we can show that these are fractals, and also there may be some chaotic behavior, and we can apply the theory of fractals or chaos. We can do many things inside the differential, many more things. Okay, so now we have Sierpinski cube. So what is this? We take a cube. So what happened in this cube? We cut inside again from the all side middle things we cut. So delete open cube of side 1/3 from middle of this cube from each side. Now we get a small side blocks here, here, here. On each block also you apply same. We get this. Repeat this process. If we repeat this process, we get now fractal like this. Okay, so we have this new fractal in 3 dimensions. So a lot of things you can do, and you can take different structure. You can think any kind of initiator you can think and apply the process, repeating process. You get different kind of shapes. Now these shapes can find through functions. I have shown just cut. So somebody say, where is the mathematics? This is geometrically easily we can do. So there is a mathematics, and this mathematics you connect to also differential equation. So step by step we will go. So now we have iterative function system. We can show, we can find fractals through function. So IFS is iterative function system. Let F1, F2, Fn be a family of contraction on R. And S is a closed bounded subset of R. K is a, you can take any order. K is any dimension. Okay, 2, 3, 4. It depends on what we have to generate. What kind of fractal we have in 2 dimension, 3 dimension, or 100 dimension. Then the system SF is union of all Fi. It's called iterative function system. So these are actually contraction. Contraction, how to define a contraction? A map is said to be contraction F is S to S if for some alpha is 0 and 1. This is the actual definition what we studied in fixed point theory, or when we study metric space or topology space, topology, same definition is here. If z1 minus fz2 norm is less than equal to alpha z1 minus z2 norm. Simple definition, everyone know about this definition. So we have these apply this. We have contraction mapping. We have set of these functions. So it is an iterative function system. Then we define. Suppose we take a 2 dimension case 2. So we define a affine transformation. So a transformation f r of the form this. So we have taken very simple 2 equations, and we have written in the form of matrices. Very simple too. Okay. First function just you ax plus by plus c. Second equation is f, okay, fxy equal to c x plus by plus f. So simple 2 equation. We can write these through matrices. It is easy to write a computer program if we write in matrices, because we have to iterate the system. So if we have in the matrix form, then we can write a program easily through any computer programming. Okay, so where A, B, C, D, E, and F are real numbers. Okay, we can write these things also in the polar form. Sometime we can convert our map in polar form, and we can generate the picture. So here we have generated some picture in MATLAB, but I don't give the detail of the how to, because this is not our aim to show this thing, but I want to show mathematics and fractals about. But we can generate this through MATLAB. So I will show you one for how to generate this. So construction of Basle funds, it is famous, very famous fractal. I have shown in the I have already shown in the beginning. So let S be a rectangle along with following 4 transformations. So these 4 transformations are contraction. So F1, F2, F3, F4, and we have variables R, S, theta, phi, E, F. So we have chosen the form of polar form. In this case, we have in polar form. So what we have, I already told, we can write this in the form, Cartesian form or polar form. Then we have this. So we have taken example. We have this data. So for this data, we have a contraction mapping F1, F2, F3, F4. So we have now F1 use S. We have S as a triangle. We have taken triangle as S. And using this parameter, we take a mapping F1 S equal to, we get R1 new mapping. On apply S on F2, we get R2. S apply on F3, we get R3. F apply on S, F4 apply, we get R4. So we get 4 new mapping. So 4 new things like that. So Basle fund can be grouped into 4 parts: R1, R2, R3, R4. So what is? We have initiated rectangle. This. All 4 mapping we will apply on this. We get 4 new sets: R1, R3, R4. Okay. So R1 is just to the this. R2 is some angle. R3 also at angle. R4 also is inside this. So we continue this process on each part, on R1, R2, R3, R4, because we have again 4 mapping. So up to 5th iteration, we get this one, 3rd one. And continue this process after 20 or 50 or 30, 40, how much complex you need picture, how many good picture you need, then you stop there. And finally, we get this fur, Basle fur. Mathematically, we say that Fn is n equal to 1 to infinity converges to Basle fur. So actually, we applying the fixed point theory, and we say that iteration going to fixed point, that is Bn. So in this case, we are applying the some theorems related to fixed point. Then we get this. Okay. So now we can say that fractal geometry can be used to make precise model of physical structure from funds to galaxy. And scientists can describe the shape of clouds as precisely as architect can describe a house. So fractals everywhere, Michael Basle have written this. Now most of things when we see using the fractal is similar like this sentence. So fractals are modeling tools for investigation of various natural and scientific phenomena. Either we have scientific things or we see the nature. So we can model a lot of things through fractals nowadays in more natural form. there are a lot of techniques exist. We can make similar picture also by other techniques. But nowadays fractals are more good than other tools. Also easily you can generate pictures through computer programming if we apply the techniques of fractals, how to generate fractals through mathematical formulas or expression or techniques. Okay. Now next thing we want to go other side about chaos. So generally what happened, we see around us most of things non-linear. So it's a non-linear world generally nowadays. Things are not very smooth, okay, nowadays, and everything become every day by day complex because of due to we see any we say network, we say mobile network or internet network or any kind of network, okay, real network or aeroplane network, okay, airlines, we can say airlines network, allowed all our network every day by day becoming complex, and we are seeing things become non-linear. So we say it's non-linear world. The real problem issues on the frontiers of modern scientific, technological, economic and social researches are non-linear. Very less are found in simple and easy to do. So in the Laplace world, everything was predetermined, no chance, no choice, and no uncertainty. So long time before Laplace told this. Nowadays, it is more accurate when we see the chaos theory. So now we come on the next. Chaotic behavior. What is the chaos and how to see chaotic behavior? So market prices are chaotic. Okay, every day we see the things around us in the newspaper or the, any kind of media we see. Okay, so we see the news about the markets. So we see market prices as well. Traffic situation is chaotic also. Any kind of traffic. Okay, we have complex situation. Weather is chaotic. Okay, people are trying to show these are chaotic, and they have developed the theory and they shared many things are chaotic. So what is difference between chaotic situation and different other complex and random situation? I will tell you. So behavior of human is very chaotic. Okay. We can see that behavior of human is very chaotic. The structure of brain is chaotic. We can see many more things. Chemical reactions are chaotic. Explosion of volcano seems chaotic. And a lot of things. Chaos exists everywhere. Okay, so what is chaos? So this is the extreme disorder, irregularity, and confusion. This is a rough definition of chaos. Extreme disorder, irregularity, and confusion. Okay. So how to see it is how to see how is it is differ from other. So this is a phenomenon that stick underlying rules behind irregular appearance. It is a phenomena based on situation. It is not a object like a fractal. Okay, it is a some behavior. It is not easy to find, but also inside the irregular appearance. But important thing is it is deterministic. We can see view of chaotic and other phenomena, how these are differ from these things, chaotic situations differ from other situations. Type of phenomena, appearance and underlying rules. So something is regular phenomena, appearance is regular, underlying rules deterministic. So there is no simple thing like this. Okay. Something is statical, it is regular, but it is based on probability. Okay. This is the second thing. Now it is we have more thing, more complex thing is random. Something is random, it is irregular, it is not a very smooth situation, irregular, but based on probability. Due to probability, we cannot say every time one situation is accurate. Anything, whatever you think. But when we have chaos, it is irregular and deterministic. Any kind of static, but it is irregular. This is very important. So this is the chaos. So we try. So this chaos have more advantage than other phenomena in irregular form. So again, there is no hard and fast definition. There is no standard definition of chaos. Okay, we can define this in form of some features. So feature of chaos. So deterministic, non-linear, irregular, sensitive to initial condition. We have these things. Okay. We have these things. Then we can say that there is a chaos. Last one is very important, sensitive to initial condition. We have to find. Other things we can recognize. Okay, it is non-linear, it is irregular, deterministic. But sensitive to initial condition is very important. We have to search. It is not every place. You have a system, but whole system does not sensitive to initial condition. In some part, may be sensitive to initial condition. Depends on, again, I am saying it depends on situation. We will see that thing. Suppose we have differential equation, a lot of parameter with equation, differential equation or any other equation, but for all parameter, there will not be chaos. For certain parameter, there will be chaos, chaotic situation. We can find chaotic behavior. Okay, so we go on this, based on this, we will see that thing. So theoretician tries to answer some question. What kinds of nonlinear system exhibit chaos? How does the behavior of nonlinear system change if parameter describe the system change? How do we decide if system is strictly chaotic and how do we describe chaos quantitatively? Yes, quantify. How to quantify the chaos? That's the main thing. There is chaotic situation, but how to quantify? How to mathematically we say there is a chaos? Because something looks like very complex, but there may not be chaos. What are the universal features found in a many nonlinear system? Are these features truly universal or are there different kinds of chaos? How do we understand this universality? What does the study of chaos scientifically and technically can perceive. What are the philosophical and methodological implications of chaos? So a lot of questions we have. Some of questions we try to answer here through some researches already have been done, and also we try to visualize something through mathematically through published paper. Everything I cannot explain because a lot of things in these questions, and our focus also to connect fractal chaos with differential equation. So here are a lot of things also associated to different kinds of scientific phenomena or with different kind of mathematics. Okay. So we start with this next thing. We try to connect now fractal and chaos with differential equations and how differential equation is studied by which way. So here we will study through dynamical system. And dynamical system, mostly we do the mathematical modeling and we get a dynamical system generally, and we write in terms of difference or differential equation. So either we get differential equation or difference equations we have dynamical system. Dynamical system also we can write in two ways, linear and non-linear dynamical system. But here our aim to study the chaos and fractal both. Fractal is exists in linear and non-linear both, but chaotic situation exists in non-linear system. So again, non-linear system maybe we can classify in two parts, discrete and continuous. But here our focus in continuous dynamical system, because continuous dynamical system is associated to differential equation, and discrete means difference associated to difference equation. But basically, this discrete system is very important because many times what happens when we have continuous dynamical system, our differential or we have differential equation, we are not able to get direct solution. What we do, we discretize, and we can find any discrete method or numerical method we can study also again. So many times we can study differential equation numerically. Also we can write in discrete form and we can study the solution. Okay, so due to this I written also difference equation, but our main focus on differential equation. But those who are interested, sometimes they are not getting a direct solution or not very easily things related to differential equation, they can use the discrete method and they can apply the numerical technique, then they can study the fractals or chaotic situation. So we can see this thing in chaos in continuous dynamical system. So in continuous dynamical system, we will see what is here. We have a lot of model, Lorentz model, Russell model, Dirichlet problem, a lot of model we have to see chaos in continuous dynamical. So I have taken some famous model so people can connect the other equations with this model and they can explain the chaos in there. Okay, so what is the Lorentz? This is a model, and in every tag most of time we take this because Lorentz scientist some way also mathematician, but not full mathematician. He was also a scientist, we can say. He has developed a model related to weather prediction. In that weather prediction, he has studied some differential equation. Inside the differential equation, they have chosen some parameter and they have got some interesting things. So first described by MIT meteorologist Edward Lorenz in 1963. So Lorenz model is given by a set of three ordinary differential equation of using the parameter. So we can say it is parameterized family. Okay, so they have chosen some parameters values where parameter P, R, B are positive real number. So I forget to write the exact number here. So after choosing some P, R, B positive real numbers, we get like this structure. This structure is well known and studied a lot of people in different ways. They have shown that is a fractal and they have found a fractal dimension actually. This is non-integer, and also they have found some other things to show chaotic behavior, maybe Lyapunov experiment, entropy, a lot of things they have used to study this model and to show that this picture is chaotic and this is the in every book you can find this. I don't want to go much detail on this model. We have another model that is Russell model in three-dimensional non-linear system of differential equation. So in the Russell some parameter E and F. Choosing some of the parameter, we get interesting pictures, fractals, or inside fractal we have a chaotic behavior. So you may have different differential equation. You can find different things. So this is a fractal, and inside this is represent that chaotic behavior inside there because for parameter value EF point to M equal to 5 point chaotic path appear with a form presented in picture. There is big mathematics behind this, okay, and more computation, and everything exists. So due to this, I have not taken anything here. So this is very famous model in all dynamical system books. There they have studied this kind of problems or in numerical methods or in differential equation. You can find this, and you can find uh, terminology behind this. Okay, so like this, we can see the this same thing in the partial differential equation. Also, fractals exist. In this paper, they try to show that origami and how related to partial differential, and these are fractals. So consider this Dirichlet problems. I have not taken any specific long problem here. Just I want to show it is existence of fractal inside partial differential equation. So what happened when we choose n equal to 2? So second picture, this is generated picture. This is just folding. Okay, folding paper looks like this, and we have this. Our aim to show the differential, not folding, but show the solution of differential equation for n equal to 2, we get like this. And for n equal to 3, we get like this. So these are fractals. These are fractals inside partial differential equation. We have a Dirichlet problem. Okay, so we go some more kind of studied to see the both in fractals and chaos. So dynamics of generalized Lorentz like dynamical system. I have told in the previous slides Lorentz model. It is not exact Lorentz model, Lorentz like model. Inside that we have chaos. And we will see that here we have good fractals, interesting fractals. So it is recently published in 2021. They have taken generalized Lorentz-like system using the 7-parameter or differential equation dx over dt hy minus x minus dyz dy over dt cx minus ky minus exz dz over dt xy minus z. Yeah. Why Lorentz like I already told, just see this in the previous slide. This one. Okay. So they have changed this model and they have done this new model that is called Lorentz like model. They told and they have studied using different parameters. So here they have taken 7 parameters. Okay. So every differential equation and system of differential equation has parameters, and based on that we can decide the solution. So where x, y, z are real variables and a, b, a and other are positive real parameters, c, d, h are real parameters. So some are positive, some are maybe negative. Okay, this information they have given the information. So based on this, they have studied a long theory behind this, mathematical theory behind this. After studying the things, they have found the chaotic behavior inside the system, and they have represented by this picture. So in the first chaotic behavior in a system in 2.1, they have seen this in xz plane in 2 dimension, and this in second is yz plane, and third one is they say bound estimate for QT extractor in x, y, z in 3 dimensions. They plotted. So these are also these pictures, also Lorentz-like pictures. Also, we have this trajectory like this, complex trajectory. Okay. All trajectories are similar than also Lorentz kind of attractor. Okay. So due to this, we have name of this also Lorentz system, and we say chaos in dynamical system, and these pictures are also Lorentz like pictures. Also, we have some more things, because many times what happened, we say mathematically, also we say graphically and generate the pictures, but how to, when we have a data and when we have parameters and we have equations, how to say there is a chaos. So measure of chaos, how to quantify that chaos. In different ways, we have a lot of theories behind to quantify the chaos. Some of them I have written here: fractal dimension, Lyapunov exponent, and entropy. So I will not go in much detail about to quantify the chaos, to find the chaos, but I will show. I will show something here through Lyapunov exponent or fractal dimension. We can see also equation, differential equation when we have complex function. We get a complex solution actually. So in that case, we study the dynamics, that is the complex dynamics. Actually, we study the dynamical system inside the complex plane. So many times what happened when we study the solution, and solution we get a in form of function that is a complex function, and we get a study of that function. So we need complex dynamics. So in that case, we have also fractal inside the complex plane. Also we have chaotic behavior actually. So in the complex plane, when we study the dynamical system, we break the plane in two parts. We say two subsets. One is Fatu set, that is a stable set. Another set is Julia set, that is a chaotic set. Fatu set is stable set, we can define like this. Fn is a normal family, means all points inside this set have convergence. Julia set is chaotic set, that is complement of Fatu. So Jf is equal to complement of complex plane. So that is complement of Fatu set. Okay. So now for this purpose, we have taken some differential equation. We have a solution. This solution is associated to complex. So zero of solution of linear equation of such order. We will study it and we will see we have fractal and there is some chaotic behavior maybe. So we have now differential equation, consider differential equation of this second order u double dash plus rz e. Here rz is defined by 1 minus 2 over z square. We get a solution that is u, that is c1 under root z j minus 3 over 2z plus c2 under root z j. This is a Bessel function. Okay. So we get this function. So we have now. So this is already long before published now. That our aim to show the fractals in differential equation. So due to this we have taken zeros of solution u of differential equation is found by using the Newton method. Because we have a solution of differential equation, we find the solution. Zeros of solution. So u is a solution. When we need a zeros, it means fixed point of Newton function. So we have this Newton function. If z is defined by z minus uz over u dash z. This is a Newton function. So find after using the Newton method, we get this function based on this formula, Newton formula, and we do the dynamics. Use the root 2 does not. Root 2 is a actually fixed point, black region of the function. So we plot the region black where this iteration does not converge. We have white region, there converges but needed more iteration. We have gray region converges after few iterations. We have this. So we have this. After this, we see these pictures. First one. When we plot, we get this. Actually, this is old picture, or that time they have published in gray language in this paper. So we don't have color of picture of it. But we take the zoom of this, we get like there are many places we can inside we can do the zoom. Different places we can, so we get a very interesting and inside very good. So in this region we have this, we take another region, okay, different region, we have this. So inside that we get a, these are complex picture but are repeating structure everywhere inside this or inside this or the third one inside, we go inside, zoom it. So these are fractals. Inside that also there may be chaotic situation. Also when chaotic situation means when we have sudden change in a system, when we change the parameter. So there may be also chaotic situation, but here we easily can recognize the fractals because in this paper they try to find a fractal inside a, to show the zeros thrown inside. So they want to show there are some fractals in different regions. Now we have differential equation related to Schwarzschild derivative. Schwarzschild derivative is differential. This is rational function. Here SDF is a rational function. We say rational. We consider family of function. If it is rational, Schwarzschild derivative rational, then we have generated this result. So I have generated this result and we consider the family. If SDF is transcendental monomorphic function of F is rational, all poles of F are odd multiplicity, all zeros of F are even multiplicity. Then differential equation. This differential equation has two linearly independent solutions, G1 and G2, and each having a finite Lemoine G1 over G. So I have generated in this equation a solution that is ratio of two linearly independent solutions. So this theorem I have generalized in for rational function. One of this result is already exists, but I have done dynamics for if this SDF is rational. So using the Schwarzschild derivative, many people have done dynamics using this equation where SDF polynomial or constant. But very few of them I have not found before me when I did this dynamics some year before. That time I have chosen rational function and I have generated this function G1. So in that case we have a dynamics. We have I have already studied dynamics of f lambda z. Z is lambda z over z plus 4 exponential z for this. Actually, this is a solution of a ratio of two solution coming from previous equation where SDF is this minus half 1 plus 8 over z plus 2 whole. So that solution I have studied like this. Here we choose an lambda. So lambda is 0 to 4. We get a Julia set. This is a complement of basin of refraction. And we have taken another lambda from 4 to exponential power 3. Then we have again Julia set. It is complement of A basin of attraction of A lambda. What are basin of attraction? This is just basin we have already studied. So A0 where all points converge to 0 in this set. So this is the basin attraction of 0. And basin attraction of A lambda, 0 and A lambda are attracting fixed point. We can define like this. Based on this, we choose different parameters, we get picture. Then we have taken lambda equal to 3.9, we have this picture. We have taken lambda equal to 4.1, we have second picture. We have taken lambda equal to 20, we have next picture. Then we have lambda equal to 20.1. It means exponential power 3, 20.0865. So here we can say that these are all fractals in complex plane. And this function is solution of differential equation in some special form. Also, here is sudden change in a parameter, small change in a parameter, we have sudden change in picture. Above left and is in the down, lambda is equal to 20 left and lambda 20.1 is right. So sudden change in this picture. So this sudden change gives us chaotic behavior. So we have here chaotic behavior. So a lot of things we have now to show the these fractals and chaos in dynamical system. So now we go on next one. A chaotic jerk system with 3 cubic nonlinearity dynamical analysis, adaptive chaos synchronization and circuit simulation have been done. This is published in 2019 and these are the authors. So they have a 3 jerk system. This system is called jerk system. They have taken 3 differential equation x1 dot equal to x2, x2 dot equal to x3, x3 dot equal to minus x1 minus x3 minus b x1 square x3 plus x1 x2 square minus x1 x1 x2 are state variable and ab are constant. This system is chaotic for a equal to 2, b equal to 0.2. They have done like this and they have chosen the system of differential equations. Then they have got this type of trajectories. So for a equal to 2, b equal to 0.2, these trajectories when they found they are chaotic. So how to see this chaotic? I already told we can find something more about this. We can study the bifurcation diagram. We can study the Lyapunov exponent. We can find the fractal dimension. A lot of things behind this if you want to quantify the chaotic situation. And to say these are actually fractals, there is no doubt. If we look, but some people say no, we are not. So we can find the fractal dimension of this. Okay, a lot of things behind this. So first thing is using the data and how dynamics is changing, we can compute the bifurcation diagram. Based on bifurcation diagram, we can generate the Lyapunov. We can find the Lyapunov exponent. This how parameters are changing. A is changing. We are getting picture like this based on x here. So here is we have different of cycles inside the bifurcation. But we will see that when we have to generate the Lyapunov exponent, we have this. So what is here actually? When we see above here Lyapunov exponent above, so in this case they have using actually different techniques LE1, LE2, LE3. Okay. So first technique is this Lyapunov exponent using this based on bifurcation diagram directly using this bifurcation data. And in this case, where is Lyapunov exponent is negative, means below the 0. There is no non-chaotic solution. Where is above the 0, this blue region, we have this here dark region in left picture. There is a chaotic solution. So using the Lyapunov exponent and bifurcation diagram to show there is the theory behind this, we show mathematically and numerically we can also find through any computer. But for specific parameter, Lyapunov exponent for discrete data, just we can define that. We can also do for function. If we have a function, also we can find. So this system is QT. The Lyapunov exponent is greater than. So I already shown in the. So a novel 3D fractional. So nowadays actually we see that fractional order, okay, fractional system and a lot of things associated to fractional. In the fractional calculus are going on. Okay, so we have fractional order. So a novel 3D fractional order chaotic system with multifarious coexisting aspects. So we have also fractional order differential equation. Inside that we have also Q and fractal. So this paper I have taken published in 2019, and we have differentiation like this. D to Q X dt. Here Q is fraction. X, Y, Z are real. X, Y, Z. A, B, C, D, and H are constant. Q is fractional order between 0 and 1. If it is 1, then it is simple equation. Okay. But less than 1, greater than 0, we have fractional order. So a lot of theories are going on related to fractional order. Okay. So we will see something. Based on some parameters we have chosen, now we have fractional order system. Based on fractional order, we have now these pictures. Here we will see phase diagram of system V coexistent of pair of strange attractor A equal to 7, B equal to 3, C is equal to 8, D equal to 0.8, H equal to 0.5, Q equal to 0.9. Using the initial value, blue, red, different ways, we can plot in different. And we get this factor in fractional system. And inside that there is a chaotic situation. We can compute a bifurcation diagram for different parameters, and we study the Lyapunov exponent, and we can find the trajectories, other trajectories to show that there is a chaotic situation inside the. So for A equal to 7, B equal to 3, but Q is equal to 0.9, C equal to 15. We have this type of chaotic attractor. C equal to 25. We have this kind of chaotic attractor. So what happened? Many times we have a solution. We can also, I already told, we can discretize and we can use the system. Okay, so we can also equation we can write in discrete form. Suppose we have taken this discrete system. I am not saying exactly how to convert, but when we have discrete forms for different parameters, we choose this. We get a this is Q. So sometimes we are not able to find a solution directly in differential equation. We can discretize and we can use the discrete system. We can write in difference form, difference equation. We can also study fractals and. Yeah. Okay, here we have taken two discrete, okay, in two variables, and theta is rotation angle. We have this. So we have done this one. So based on this, so okay, so for this we go on next model related to system of three difference equations. Okay, we have three difference equation now. So in this case, we have get a very interesting picture like this. this parameter value E equal to 0.2, iterating under the certain condition, we get interesting chaotic form like a seashell. Okay, it is not a painting, it is not a designing, it is just of a space parameter inside this system. So many times what happened, we have differential equation, we can discretize, we write in difference form or directly maybe difference form, and we can use similar theory, almost similar type of solution. Most of time exactly similar way, we can find a solution or difference equation also, and we can generate a fractals and we can see chaotic situation inside. So we are now near to finishing our things. So we are giving some references here, and a lot of references are available. Also, I have already mentioned inside the talk, and these are more references, and these are also references. So thank you very much for listening me here. So if there is any question, anything.
Yeah, I request participants if you have any questions.
So, Professor Sajid, I have multiple questions. So the first question is, so how much study is done for chaos in partial differential equations? Chaotic behavior in partial differential.
Just 1 minute. Your voice is not coming. I do by other system. Okay, now tell me.
Yeah, so I am saying that how much study has been done for looking at the chaotic behavior in partial differential.
Just 1 minute. Just yes. Now tell me.
Yeah, so how much study has been done for studying the chaotic behavior in partial differential equations?
Yes, actually, in the many things have been done in partial differential equation, but I have not studied so much because I have just given the too much. I have a lot of things I have seen, but
Yeah.
I have not studied in that direction.
Okay. So my second question is, what do you think is the role of computer science in chaos and fractals? Because I think some
Yes,
of
yes, this is a very interesting and good question because chaos and fractals are not without computer.
yeah.
And nowadays is a very interesting is quantum chaos and quantum fractals.
Yes. Yeah, from that angle I asked that question. So
Yes, actually the talk will become very long. Otherwise, due to this I have not taken many things.
yeah,
So
okay.
otherwise I could not explain what is the fractals.
So it was
I
very
can-
good talk actually. It was very good talk. I loved each and every bit of it. So another
So I am very interested in quantum chaos. A lot of things happened, but it is behind of my uh, study because we don't have much time to go inside the deep knowledge of quantum.
yeah, we can talk about it, no problem. We can talk about it offline. Anyway, so my another question is, as you know that there are certain functions, say suppose on the real line, which are self-similar, right? If you draw their graph, they are self-similar, right? So do you think that for most of the fractals that we observe, we can find such functions, say maybe in the higher dimensions or something like that?
Yes, yes. In the high dimension, we can find, but we have to use the IFS
Hmm.
because, and also we have to find the fractal dimension that should be non-integer.
Okay. So there has been some studies on that as well, right?
Yes, yes.
Okay. Yeah, I think that's all. I think so. We can discuss couple of things. I think there are many interesting problems that comes to my mind. We can discuss offline, right?
Yes, yes. Actually, a lot of things inside also different, but we here our aim to show some glimpse of fractal. Those who do the workshop, they must understand fractals and cures, then they can apply.
Yeah.
So,
Sure. Thank you.
Yeah. Is there any other participant? Okay. So thanks to Professor Sajid to give this nice talk.
okay.
I had a course on fractal interpolation at IIT Kanpur under Professor GP Kapoor during my study. So there I learned that
I tell you on this.
then,
This is also in the interpolation. Fractal interpolation is very important nowadays. A lot of approximation and also compression. People are doing through interpolation, fractal interpolation. And Professor Chan, okay, he is
IIT Madras.
in the IIT Kanpur. He is in IIT Madras. He is
Yes.
we can say in India, father of interpolation, in fractal interpolation. He has published in the first paper in IIT Kanpur in Shyam,
Yes.
fractal interpolation.
Yeah. So in that course, we have learned that fractals are nowhere differentiable. So, and this is an opportunity to see that fractals and differential equations relations here. Yeah.
Yes, actually, yes. If you go in the function, then you say, but fractals is not always inside the through functions. We have also fractal without function also. Because fractals exist everywhere, all fields. So maybe without function, we can study also fractals.
Okay. Yeah. So I thanks Professor Sajid again to give this wonderful talk. Yeah.